Hello, this is R, and R software, and I'm on a Linux Ubuntu based machine, and we're going to plot the exact distribution of the sample range for any continuous function. And I'm specifically going to limit my continuous functions to ones that have built-in functions in R. So we're going to generically let xi be any density f with CDF cumulative distribution function capital F. And the joint density for the first order statistic and the nth order statistic is this. It can be written as this. And the sample range, as we know, is the largest observation in the sample minus the smallest observation in the sample. So we take this joint density of y1 and yn and transform it or map it to R. And that ends up being this function here. So we take, it's essentially this function with certain values plugged in it. And I'll provide a link to this proof. It's very straightforward that this indeed is the density function for the sample range for any f or any continuous distribution f. So, well, with this, then we create a function. So this function here, I'm going to do it for the normal population first. So we create a function where R is our variable, N is our sample size, M is the mean, S is the standard deviation, and we're going to integrate a function. And it's N times N minus 1, which is this, times certain values plugged into the density. Same here, certain values, R plus X, and then the cumulative distribution function is P norm, and we're going to subtract off P norm, raise it to the N minus 2. And we're going to integrate it over, from infinity to infinity. So let's load this value, load this function, and this is it. This is the probability density function for the sample range for a normal distribution. So let's go through an example. Here we're going to have sample size of 10, mean is 1, standard deviation of 1, and we'll generate a sequence of numbers x, and we're going to create, we're going to calculate the density for each x. So we go, the range has to be positive, so it goes from 0, and I go out 8 standard deviations, and then we store those values in R, which I'll show you. So then we calculate it. Now let's plot it, and there it is. There is the exact distribution for the sample range when you have a normal distribution, sample size 10, mean 0, standard deviation 1. And this can be conducted, and if you think about it, so here the mean is roughly 3. So, if you think of small sample of 10, you're not going to see the whole gamut of under the normal distribution, so the range is probably a little smaller. But if we calculate it for, say, 100, a sample size of 100, and go through the same process, then the mode is around 5, which makes more sense because the whole, there's usually 6 standard deviations, which is S, but you don't see the extremes on either end, so it's, the range is in this area. So it seems intuitively makes sense, But let's conduct a quick simulation. So I'm going to create a function that calculates the range. So I'm going to create a matrix, and each row will be a sample. So the number of columns will be the sample size, and then we just want to calculate the max minus the min of each row. So in this case, let's do we'll do sample sizes of 10. We're going to do this 10,000 times. So we're going to create a matrix that has 10 columns, because number of columns is a sample size. So the first row will be sample 1, second row will be sample 2, all the way down to 10,000. So this matrix will have 10,000 rows and 10 columns. And then it creates the range and stores it in temp. So if we look at a histogram of the range values that we obtained from our simulation, it's this. Now let's plot the exact distribution right over the top of it, and it couldn't be more accurate. Okay, so let's redo this for, let's say we have sample sizes of 100 this time, standard deviation of 5, and really the mean value doesn't matter, so I'll leave it at 0. So let's redo this. So here the matrix is going to be 100 columns and 10,000 rows, and then we look at this. We look at the sample histogram of those values, and then plot the exact distribution right over the top of it. So here, let's do something a little bit different. Let's add in some, let's say 45 breaks. So here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12 little boxes, but let's add in 45 and see what that looks like. So that's this, and then we plot the exact distribution over the top of it. It's right on the money. Now this can be duplicated for any continuous distribution. We use the normal, but now let's do it for the chi-squared. So this function here is exactly the same, except for these functions here. Instead of saying d norm, it says d chi-squared, d chi-squared. Otherwise, it's the same. Oh, except for the parameters. In chi-squared, you need degrees of freedom, and in normal, you need the mean and the standard deviation. So there's another difference. So let's load this value, load this function, and let's calculate this for sample size of 50, degrees of freedom 10, and plot the exact distribution for the sample range when it comes from a chi-squared with 10 degrees of freedom. And that's it. To me, that is just so fascinating that we can do that. So now let's conduct a simulation very similar to the other one. Instead of generating random normal variables, we're going to generate chi-square distributions. That's what this function here does. It's generating random chi-square. So let's say sample size of 100, degrees of freedom 22. Let's create the range distribution, 10,000 reps. Look at a histogram, and then plot over the top of it the exact distribution for the sample range, and it's right on the money. So again here, let's add number of breaks. Let's say 45 again. That seemed to be a good number. And then we calculate the exact distribution right over the top of it. So that's pretty neat, pretty fascinating. So I could keep doing this and just replace this with another continuous distribution, and the built-in continuous distributions in R are these: the beta, Cauchy, chi-square, which we did, exponential, f, gamma, log normal, normal, students t, uniform, Weibull. And you could also just write your own function, and it would be, and you could do something similar. So hope you enjoyed this, and I will talk with you later.